Our lecture for today is to investigate the properties of a parallel resonance circuit. What is a resonance circuit? An electrical circuit that combines capacitance and inductance in such a way that a periodic electric oscillation will reach maximum amplitude. Or, an electric with inductance and capacitance chosen to allow the greatest flow of current at a certain frequency. Fr is equal to 1 over 2 pi multiplied by square root of LC. In a tuned circuit such as a radio receiver, the frequency selected is a function of the inductance L and the capacitance C in series. What about the resonator? A resonator is a device or part that vibrates with and amplifies waves. It naturally oscillates at some frequencies with greater amplitude than at others. The noun resonator has three meanings. 1. A hollow chamber whose dimensions allow the resonant oscillation of electromagnetic or acoustic waves. 2. An electrical circuit that combines capacitance and inductance in such a way that a periodic electric oscillation will reach maximum amplitude. 3. Any system that resonates. Each of our major organs has its own resonant frequency depending on its mass and the elastic forces that act on it. Pain or discomfort occurs in a particular organ if it is vibrated at its resonant frequency. We find that excessive vibration often occurs in motor trucks. It results in fatigue and discomfort and may cause visual disturbances. The vibratory frequency of motorized vehicles is usually 8 Hz or less. As might be expected, aircraft and space vehicles have higher vibratory frequencies. Simple parallel tank circuit resonance. A condition of resonance will be experienced in a tank circuit when the reactances of the capacitor and inductor are equal to each other. Because inductive reactance increases with increasing frequency and capacitive reactance decreases with increasing frequency, there will only be one frequency where these two reactances will be equal. As shown in this photo, simple series resonance, a similar effect happens in series inductive or capacitive circuits. When a state of resonance is reached, capacitive and inductive reactance is equal, the two impedances cancel each other out and the total impedance drops to 0. As shown in this photo, since we know the equations for determining the reactance of each at a given frequency, and we're looking for that point where the two reactances are equal to each other, we can set the two reactance formulae equal to each other and solve for frequency algebraically. XL is equal to 2 pi FL. XC is equal to 1 over 2 pi FC. Setting the two equal to each other represented a condition of equal reactance resonance. 2 pi FL is equal to 1 over 2 pi FC. Multiplying both sides by F eliminates the F term in the denominator of the fraction. 2 pi F square L is equal to 1 over 2 pi C. Dividing both sides by 2 pi L leaves F by itself on the left-hand side of the equation. F square is equal to 1 over 2 pi to pi LC. Taking the square root of both sides of the equation leaves F by itself on the left side. F is equal to square root of 1 over the square root of 2 pi to pi LC. Simplifying, F is equal to 1 over 2 pi multiplied by the square root of LC. The medical applications of resonance. Nuclear magnetic resonance. Nuclear magnetic resonance NMR is a non-invasive means of obtaining clinical images and of studying tissue metabolism in vivo. Bloch and Purcell independently discovered NMR in 1946. 6 years later, they were awarded the Nobel Prize for their achievements. Since then, the development of NMR spectrometers and NMR scanners has led to the opening up of whole new branches of physics, chemistry, biology, and medicine. A new diagnostic technique utilizing magnetic fields shows great promise. It uses an effect called nuclear magnetic resonance NMR and is called NMR imaging. The nuclei of some atoms have small magnetic fields because of their spins, just as electrons do. Usually, these spins are randomly oriented, but when placed in a strong magnetic field, they align themselves with that field. The directions that these tiny magnets point can be altered by sending in a radio signal. By measuring the amount of radio waves absorbed and re-emitted, it is possible to measure the location and abundance of certain elements. It is a type of resonance since only certain frequencies of radio waves will work, depending on the type of nucleus and the strength of the magnetic field, hence the name NMR. One element that can easily be detected using NMR is hydrogen, which is found in great abundance throughout the body. To make an NMR image, one places the patient in a strong magnetic field. As we see in this photo, radio signals are sent into the patient and their absorption and re-emission are measured and then analyzed by a computer. An image is constructed by the computer. The resolution of the image is not as good as that of some X-rays, but NMR is still in an early stage of development. It has two distinct advantages over X-rays. First, it has none of the hazards associated with X-rays. Second, NMR gives information related to the functioning of organs, whereas X-rays are sensitive to their densities, which is not always a good indication of organ function. NMR imaging promises to be very useful in detecting cancer and other degenerative diseases and seems certain to become an increasingly important diagnostic tool.